So I'm going to talk about solving exponential and logarithmic equations. And some of this stuff I've already touched on in previous videos, and others have not talked about yet, but we're going to use the ideas of the properties of logarithms and the rules of logarithms to solve different types of equations. Now, the principle of exponential equality is one that was talked about in a previous video, and this one basically says that if you can get the bases the same on an equation, then you can set the exponents equal to each other. So if we have this equation 4 raised to the 3x minus 5 equaling 16, the idea is that we get the bases the same first, and we rewrite these equations, and in this case it would be with a base of 4. So I'm not going to mess with the left-hand side here, but I'm going to rewrite 16 as 4 squared. And now this principle of exponential equality says that since the bases are the same, we can just go ahead and set the exponents equal to each other and solve this equation. Okay, so I'm not going to spend any more time on that because it's something that I have already talked about. But, that's always a first step if you have one term on each side of the equation. So always take a look, and see if you can simply just reduce each base to the same base. So the principle of logarithmic equality is something we haven't touched on yet. But for any logarithmic base a, and for numbers x and y that are greater than 0, if you have x equaling y, then you can take the log of both sides. Is kind of how I read it. So, you can kind of think of a log as an operation almost. Notice that the base has to be the same to do this. And also notice that it doesn't specify what the base is. You can use any base that you want. Now, you're going to want to either use the common logarithm, log base 10, or the natural log, because those are ones that can easily be computed using any calculator. So let's take a look at a couple examples on when you would use this principle of logarithmic equality. It's always nice to be able to get your bases the same, but most of the time that's not going to be able to happen for you. It's always a good idea to take a look because that makes it a little bit easier, and usually you can get a more exact answer. But there's no way we can get a base of between 5 and 12 for them to have the same base. So what we're going to do is just take the log of both sides, and that's something that the principle of logarithmic equality says that we can do. So I'm just going to, you should pick what you're going to use, and your choices really are log base 10 or natural log. And it really doesn't matter which one you use. I guess usually if I'm dealing with an e inside of my equations, then I'll use natural log. Otherwise, I usually use the common log. But I'm going to take the log of both sides. And remember, log by itself is log base 10. Now I'm going to use the power property rule on this left-hand side and take our exponent of an x out front. Okay, and now we're just going to treat it like a normal equation, and we're going to divide log base 5 on both sides. Log of 5 on both sides. So x equals log of 12 divided by log of 5. Now you are going to have to use a calculator to figure this part out, but when you punch this in, you should get the approximate value of 1.5439. It all depends on where you want to round it. Now this number, is just like any other solution to an equation. If you plug that in, you should get an equivalent statement. Now, just keep in mind that this is not approximate. Almost everything that you're going to come up with is some type of irrational number, and we're going to round it to some decimal spot, and it's not going to be exact, but that is the idea still. So for the next couple examples, we're going to talk about using the logarithm of the base to a power. And that states that for any base a, log base a of a raised to the k power is just k. So it's kind of like, these are kind of inverses almost. So I'll give you an example of that. Log base 3 of 3 to the 7th power is 7. Okay? Log of 10 to the 3rd is 3. Okay, because remember, log by itself means log base 10. And now, if you look at your calculator, the log button is kind of connected to a 10 raised to the x button. Okay, and that's because they're inverses. And likewise, if you find the natural log button, that's kind of connected with an e to the x button. So we're going to use this idea to solve equations that involve the number e, or like the second example that I did, having a number 10 raised to some exponent. So you could definitely go about doing this problem like we did in the very first example. But if you understand the idea of the previous slide that was talking about the logarithm of the base to a power, then you realize that the number e and the natural log are inverses of each other. So if we take the natural log of both sides of this makes it into a very simple problem. Again, you're going to have to use your calculator to figure out what the natural log of 1500 is. But the whole reason that I picked natural log here is because when we take the natural log of the number e, we're just left with its exponent. Now you have to find the natural log of 1500, and that's 7.3132. And now we're going to divide both sides by 0.06. And we get t equaling 121.887. And remember, this is just an estimate. We have to round on that. So, keep in mind of this situation. So one thing you want to keep in mind when solving exponential or logarithmic equations is that you want to get them down to as small as possible, as condensed as possible on each side. Because when you take the logarithm of, when you're solving an equation, you're really taking the logarithm of each side of the equation. So you don't want a bunch of terms running around. So really the first step in all of this is to get everything that's not part of the base and exponent all on the other side of the equation. So I'm going to start off by subtracting 5 here and get 3e to the x equals 21. Divide by 3, so e to the x equals 7. And now since we have this number e, I'm going to take the natural log of both sides. So the natural log of e to the x equals the natural log of 7. And again, we have this idea where, natural log and e are kind of like inverses, and you're just left with the exponent, x, in this case, and that's going to equal the natural log of 7, which you find to be 1.9459. Okay, here's a very similar example, and again, get all numbers that are not the base and the exponent to one side of the equation. So I'm going to start off and subtract 30 and have 10 to the 2x power equals 1220. And now, this is as condensed as it gets. You know, we can't divide by 10 because that's not what's going on anymore. But, you know, we have this base of 10, and so if you can remember that log and 10 are almost, you know, kind of like inverses, we can take the log of both sides, the common log of both sides, and just like in the previous examples, these kind of cancel each other out, and you're just left with whatever the exponent is, 2x in this case, and that's going to equal the log of 1,220, which is 3.0864. We're going to divide that by 2 and get x equaling 1.5432. So, you know, so far we've gone over if the bases are something that you can make equal, then you can set the exponents equal to each other. You know, we can now, if we have one term on each side and we cannot get the bases equal to each other, we're allowed to take the log or the natural log of both sides and solve from there. Okay. If your equation has the number e in it, you're going to want to take the natural log of both sides. And if it has a 10 raised to a power, we're going to want to take the log of both sides. Now make sure on those last two things I said, make sure you get all the numbers on one side that are not e or 10. So now we're going to move on to some examples where we're going to use the properties of logarithms a little bit. I do want to add a little bit to this idea of the logarithm of the base to a power because we can kind of use it in a different way. But similarly, we want to get all numbers on one side if at all possible, or at least as close as we need to. So I'm going to subtract 6 from both sides and have 4 to the log of x, or 4 times the log of x, equaling -1. And now, I'm going to divide by 4 and have log of x equaling -1/4. And now the whole idea here is that log base 10 and raising 10, and having a base of 10 are kind of like inverses. And so just like we could take the log of both sides, what we can do here is, kind of set these equal to each other as if they were exponents. Okay? And since these are kind of like inverses, on the left-hand side we're just left with x, and that equals 10 to the -1/4 power. And we can just type that into a calculator and get 0.5623. And likewise, we can do the same with the natural log. Instead of using 10 as our base and each side as our exponent, we're going to use e as our base and each side as the exponent because we're starting off with a natural log. So again, I want to condense this as much as possible, so I'm going to start off by dividing 5 and have the natural log of 2x equaling 3. And now I'm going to write these as my exponents, and I'm going to choose the number e because they're kind of like inverses. And again, this is nice because we're just left with this 2x on this side and e to the third, and we just have to figure out what e to the third is. And so then we have 2x equaling 20.0855. We're going to divide that by 2 and have x equaling 10.0428. And one of the very first things that we learned about logarithms was the whole idea where we can switch it around into its exponential form. This equation starts us off in our logarithm form, and it's read log base 4 of 8x minus 6 equals 3. Okay, and remember, a logarithm is an exponent, so our exponent is going to be 3 here, and our base is going to be 4. So we're going to rewrite this as 4 raised to the third power is equal to 8x minus 6. Okay, and that's just like the definition of logarithms. And now we're just going to solve this as a normal equation. And 4 raised to the third power is 64 equals 8x minus 6. We're going to add 6 to both sides and have 70 equals 8x. Divide everything by 8. So x is going to be 70 over 8. And that reduces to 35 over 4. So for this example, we're going to use the idea of the product property of logarithms, and that's talking about how adding and multiplying are related. So we can, since we have the same base on both of our logs, we can rewrite this as one logarithm, log of x times x minus 3 equaling 1. Okay, I'm going to now switch this into its exponential form. Remember, this is a base 10. So this is really 10 to the first equals x times x minus 3. And now I'm going to solve by distributing x. So we have 10 equals x squared minus 3x. I'm going to get this set equal to 0. So x squared minus 3x minus 10 equals 0. And now we have a quadratic. And you're welcome to do the quadratic formula. But I know that this does factor. And I'm looking for numbers that multiply to give me negative 10 and add to give me negative 3. So that'd be a negative 5 and a positive 2. And set both of those factors equal to 0. And I find that x equals 5. And it also can equal negative 2. Okay, so now we're going to use the quotient property of logarithms. And again, this works only if the bases are the same. And that's talking about with subtraction and division being related. So we're going to rewrite the left-hand side as one logarithm, log base 2, of x plus 7 over x minus 7, equaling 3. Now we're going to change that to its exponential form. So base of 2 raised to the third power equaling x plus 7 over x minus 7. Okay, and so then we're going to, multiply through by, or cross multiply, however you want to think about it, by the denominator x minus 7. So it's going to be 2 cubed times x minus 7 equaling x plus 7. 2 cubed is 8. We're going to distribute the 8 and get 8x minus 56 equals x plus 7. Subtract x from both sides and have 7x minus 56 equals 7. Add 56 to both sides and get 7x equaling 63. Divide by 7 and x equals 9. Okay, on this example we're going to use a couple different properties here. The first one is the product property. Okay, and so then we're going to rewrite the left-hand side as log base 7 of x plus 1 times x minus 1. Okay, and all of this is inside the brackets here. Okay, and so now we're going to use this idea of the principle of logarithmic equality, and it kind of in the reverses of the way we've been using it. Since the log base 7s are the same here, same base, and there's nothing else going on in the equation except for one big logarithm and another logarithm, we can set the insides equal to each other. Okay, now I'm going to FOIL the left-hand side for x squared minus 1. I'm going to add 1 to both sides, get x squared equaling 9, and take the square root and get x equals plus or minus 3. Okay, so the principle of logarithmic equality can be used in either direction, right? You can take the log of both sides of an equation, or if the log has the same base, we can get rid of the log part and just deal with the other numbers.